In the previous video, we looked at angles. We looked at it in a very general sense by looking at two lines intersecting and defining what those angles were. Then we looked at two parallel lines and intersecting a third line on that. We're going to build upon the principles and properties that we found coming from those two parallel lines and intersecting line. And the basic principle that a straight line has an angle of 180 degrees. Then we're going to translate that to look at polygons, a shape with multiple sides. And we're going to try to relate the number of sides on my polygon to the sum of the internal angles, the angles within that shape. So let's take a look at the parallel lines and the line intersecting again, and start building our different polygons. In the previous video, we showed that if we have two parallel lines, these green lines, intersected by a third line here, that we can identify two distinct angles, alpha, 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 and then beta, 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 beta. So we can see clearly which angles are the same. And then we can also clearly see that alpha plus beta will give us 180 degrees. We're going to use this concept and build a four-sided object, a quadrilateral, and show what the internal angle sum is. So we're going to start with the easiest one. We're going to have two parallel lines, and we're going to connect the edges of these such that we have a set of right angles. So these are 90 degrees. Remember, this is also known as lines that are normal to each other, right? So I can rotate both the green and black line in the same manner, and they will still be normal to each other. But the easiest way to look at it is one set is vertical and one set is horizontal. In that case, these are 90-degree angles. Okay, if I connect this edge over here, or these points over here, I'll get 90 degrees, right? So I basically have a rectangle. Not very interesting, but the internal angles, these are the internal angles, right? Exterior angles will be out here. We're mostly interested in internal angles. I have four 90-degree angles within my rectangle. We'll want to see if the sum of this a four-sided object remains 4 times 90 degrees. So let's take a look at a little bit less conventional object, a parallelogram. So we're going to build it up with, again, two parallel lines in green, but we're going to shift it so we don't get these 90-degree angles anymore. So I can draw one of this third edge here, and I can extend it. So basically this looks like two parallel lines intersected by a third line, just like I had over here. Okay, and I can finalize, and so full parallelogram has two sets of parallel lines, right? So these two green lines are parallel to each other, these two black lines are parallel to each other. So it's similar to what we had in the rectangle, but we shifted it. So these angles are definitely not 90 degrees. So how can we look at these angles? Well, it'd be useful to know which angles are equal to each other. Right, so if I extend all the lines, if I call this angle theta, what other angles in this whole system are also equal to theta? Well, the this green line and this black line are intersecting, so I know these two angles are equal to each other. So that's theta and that's theta. You can look at this cartoon over here and also recognize that these angles are also equal to theta. And then these angles are equal to theta, and these angles are equal to theta, right? If you're ever confused because the angles look similar, just exaggerate it like I have in this cartoon, where one set of angles are the acute angles, less than 90 degrees, and the other set is greater than 90 degrees, obtuse angles. then even just physically looking at the angle size, you can tell which ones are the same and which ones are different, right? Okay, so if this is theta and this is theta, we can define some meaning behind this angle. We know that this angle plus this angle must equal 180 degrees. So I can call this phi, or 180 minus theta. Well, I can do the similar thing right there. This theta plus phi here must equal 180 degrees because of this straight black line. Or you can even look at this as straight green line, this theta, and this phi must equal 180. So I have theta, theta. My internal angles are 2 theta and 2 times phi. So this also is the same as 180 plus 180, which is 360, just like I have here. 180 plus 180 is 360. So far it's consistent. What if one pair of my lines are not parallel? So I can have the 2 green parallel lines here. I draw an intersecting line here. It's still true that theta and phi add up to 180 degrees, right? So this is basically this side of the parallelogram. And if I connect these lines here, this will be different, right? This line is not parallel to this one, so this is not going to be phi or theta. We'll call it gamma. Well, I know that this angle here, because this line intersects 2 parallel lines, these 2 angles here must equal 180 degrees. So even though these lines are not parallel to each other, this total internal, the 4 internal angles of this this 4-sided object is still 360 degrees. So I can generalize it and say any quadrilateral, any 4-sided object, regardless if any of the sides are parallel or not, will have a total internal angle, or sum of their internal angles be equal to 360 degrees. So let's build upon this and look at a 3-sided shape, a triangle, and let's see if we can see similar patterns. So we know that the sum of any quadrilaterals for internal angles is 360 degrees. Let's see if we can build upon this and relate it more generally to a triangle as well. How do I relate a quadrilateral to a triangle? I can split it down by matching corner to corner. Now I have 2 triangles. This is a rectangle, so I know each of the internal angles of the rectangle is 90 degrees. So when I split it down the middle, this is 90 degrees, and these are 45 degrees, 90 divided by 2. So it does make sense that for each of these triangles, the sum of the internal angles is 180 degrees. So 360 divided by 2. Can I generalize it? Let's take a look at a parallelogram. If I split this one, I get 6 internal angles. I know that the sum of all these is going to be the same as my internal angle sum of a quadrilateral, right? So alpha plus beta plus gamma plus alpha plus beta plus phi plus gamma plus psi plus theta is equal to 360 degrees. So I can't yet say that alpha plus beta plus gamma is 180 degrees and phi and psi and theta is 180 degrees. I just know the sum of all of them is 360. So how can we be confident that each triangle has an internal angle sum of 180 degrees? Well, we can go back to look at our parallel lines. If we look at these parallel lines and we split it with one line and then a second line, and we make sure one of the intersection points involve both of these intersecting lines, then we basically have a triangle right here, right? And so before we look at the internal angles of this triangle, we can look at the angles that are developed here, right? These 3 angles. So I have alpha, gamma, and beta. Well, the sum of these 3 angles is the angle of this green straight line. And what's the angle of that? 180 degrees, right? Then I can see and relate these two remaining internal angles of this triangle and how they relate to alpha, gamma, and beta. Well, I know this internal angle is gamma, that's defined. This angle right here, this is these two green lines are parallel lines intersected by this black line here. From looking at the parallel lines intersected by a third line, we know that if this is alpha, this is alpha, this is alpha, and this is alpha. So we know this is alpha. Similarly, we can look at this red line intersecting these two green lines, and then we have beta. This is beta, this is beta, this is beta, and this is beta. So I have alpha, gamma, and beta as my internal angles of my triangle, alpha, beta, gamma as my angles of a straight line, so we know it's equal to 180 degrees. Therefore, any triangle is going to have a internal angle sum of 180 degrees. So we see that four-sided object, internal angle is 360. Three-sided object, internal angle sum is 180 degrees. Next, we're going to take a look and see if we can generalize this to more sided objects. And can we find an equation that nicely describes what the sum is? So first we're going to look at a pentagon, a five-sided object. And I want to understand the sum of the internal angles here. I'm going to use the fact that I know that a triangle has a sum of internal angles of 180 degrees and try to basically make this a number of different triangles. So the way to do that without creating artificial internal angles is to pick one point and to create all the sub-triangles having that as a common point. Okay, so in doing that, you're not creating any new intersecting lines. So if I choose this point, I draw lines to each of the other points. Two of those lines are just going to be edges of the pentagon. The other two are going to split my pentagon into three triangles. We can see that the internal angles that are created in the triangles are the same internal angles, or at least the sum of them will be the same as the sum of the internal angles of the pentagon. So because of that, I know that my pentagon's 5 internal angles is equal to the sum of the 3 triangles' internal angles. So I could just say 3 times the sum of each triangle's internal angles, which is 180 degrees. So the pentagon's internal angle sum is 540 degrees. We can do the same thing for a hexagon, right? So we have 6 sides now. We choose a common point and we split it up. Now we have 4 triangles. Because of that, the sum of the internal angles of my hexagon is just going to be 4 times, because 4 triangles, 4 times 180 degrees, so 720 degrees. So we can generalize this now, right? A quadrilateral, a 4-sided object, was 2 triangles. So we can basically say the sum of a n-sided object is equal to n minus 2 times 180 degrees, right? So a quadrilateral, 4 sides, 4 minus 2, 2 times 180 is 360. A triangle, 3-sided object, 3 minus 2 is 1, 1 times 180 is 180. Pentagon, 5-sided, 5 minus 2 is 3, 3 times 180 is 540, and so forth. And we can expand this to a heptagon and to an octagon, and the same principle holds true. So just using the fact that we have 2 parallel lines and a third line intersecting, and that a straight line has 180 degrees, we were able to define this general rule for the sum of internal angles of any polygon. And this becomes very useful when we're looking at very complex systems and we're trying to figure out the angles of systems or the lengths of components. So geometry paired with trigonometry is a very powerful tool for physical systems and explaining different physical properties. And we can take a look at some examples in future videos that will show how this principle is used in application.